Welcome to this series on computer-aided modeling. This recorded video follows the previous one where we showed through a simple example the main features of MOT or the introductory features of MOT. This recorded video follows also the same procedure, but we are going to use a more detailed model and additional features of MOT. So as we talked about last time, the MOT is a combination, is a modeling test bed where the human and the computer work together, where each of them do the parts that they can do very well. And the result is that the model is developed very fast. The starting point is that a model has been derived and we have the equations. Then the 5 steps we will follow are import the model into MOT, translate the model, analyze the model, link and solve the model, and finally check the results. The model we are taking is a model for a semi-batch reactor that has a heat exchanger inside and where the temperature is controlled. A reactant A enters with a certain composition, and the reaction is a series reaction where A is converted to B, which is converted to C. So all the information of this model is actually taken from the book Elements of Chemical Reaction Engineering by Scott Fogler, published by Prentice Hall. In the different versions of the book, the one that we have taken the model equations are example 9.8. In other versions that can be different, but one version of the edition of the book will have 9.8 is the example. So all the equations are given, and let's look at the equations. In MOT, we classify the equations in terms of differential equations, algebraic equations, partial differential equations, and so on. So in this model, we have balance equations, which are differential equations for mass balance, for energy balance. So it's a lumped parameter model with ordinary differential equations. And then the other equations are algebraic equations. These are in the green and black boxes. The equations in the black boxes, we classify them as constitutive equations, and the equations in the green box, we classify them as conditional equations or defined equations. So this is the model. And then the model has a number of parameters and variables whose values need to be specified. Those that are marked in red box, they are the parameters, and the others are variables. The difference between the parameters and variables in MOT is that if it's a parameter, then during regression for parameter estimation or for optimization, the parameters could be changed in the optimization loop. So with this very brief introduction, we will now go into MOT, and we will introduce the model, and we'll follow all the steps. In developing a model, there is a workflow which starts with phase 1, defining the objectives of the modeling, then model construction, model identification, discrimination, model evaluation, model application. We will not follow this because we are directly developing the model object. So we will not use this workflow. So we are at the MOT main screen. So the first thing in MOT then to do is to create the model. That means import the model. We do this by going into View Original Model, and there is the template for it where we have to give the equations. We can import a ASCII file, we can import an XML file, and another option is if we have the equations already written out as a text file, like in a Word document, we can simply copy. We copy the equations, and then we paste it. And the syntax was already explained before, just very briefly. The mark sign here on column 1 indicates that this is a comment, and then you just write the equations. And if the equations start on the left-hand side with a D, the first variable, and then equal to sign, that's the ordinary differential equation. Otherwise, it's algebraic equation with one variable on the left and all the others on the right. This would be an explicit algebraic equation. If there is a 0 on the left-hand side, then it will be interpreted as an implicit algebraic equation. So here, all these are explicit algebraic equations. So we have algebraic equations and ordinary differential equations in this model. And what we can also see is that all the data is given in terms of explicit algebraic equations. We will come back to this afterwards. So once we have given this, put the equations into the View Original Model, we have to accept the model. So we go here and accept the model. And in this example, we are not going to use compound data from a database. So we have given all the data in the equations. So we say that compounds are not used in the sense that they're not obtained from the database. And then we say, okay, so now the model has been translated. And we can see each equation like this. So the next step after the model has been translated is to analyze the equations or analyze the model. And in the analysis of the model, we also need to select the actual classification of the model. By default, MOT puts all of them as parameters except for the explicit algebraic variables. So we know that we have T is a differential equation. So it's a dependent variable. CA is a dependent variable, CB and CC. And small t is a time, which is a parameter. It actually does not matter here. You will see later. So based on this information and the explicit equations, MOT creates the incidence matrix where each row is an equation, each column is a variable. And then it's a nice lower tridiagonal form for each of the algebraic equations. And then the light blue color indicates the 4 differential equations. So now with the equations given, what we need to do is to also assign the dependent variables to the differential equations. Note that here it says we have 4y, but dy dt is 0 because the differential equations have not been assigned. So we go to relate dy dt to y, and then we say dt is related to, t is related to dt, ca is related to dca, cb is related to dcb, and cc is related to dcc. And now we come out of here, and now you can see that it says 4 differential equations related to the 4 dependent variables. And the degrees of freedom are 0, which means that we are ready to solve the equations, the problem. But remember that this is a differential initial value dynamic model. So we need to give also the initial values for the 4 dependent variables. And this we do by going into set variable value, where the dependent variables are listed here. Then the dependent primes are listed here. The explicit variables are listed here. There are no known or parameters because all of them are given here. So what we have to do is to give the initial temperature, which I know is 298, and the initial concentration of A is 1. This is also given in the book. So we give this, and we are ready to do the simulation. So we need to then choose a solver and then start the solver. But before that, we go to the solver page and we select variable trace, chart trace, and then we select which variables we would like to plot. So we will like to plot the 4 state variables, that is the temperature and the 3 compositions. And we have to save it. And now we need to connect to the solver. So we go to the solver option. There are different options. I'm just using one of them. And we have the solvers for algebraic equations, for DAE, dynamic systems, optimization. This problem is a first order ODE system, or index 0 or 1, depending on how you would like to define. So we have 2 methods here. We will choose the BDF method. I will change the time scale to 0.02. And I will say we will have 300. So we can give different ways. So by giving a scaling of the time and the number of steps, we define what would be the end time. And there are different ways to do it. And of course, the step sizes are not going to be the same in all cases. So now we are ready to run the simulation. So in order to do the simulation, we click on solve. We say we will save this as test Zoom. So it has done the simulation. Now it's very fast. So the temperature moves like this: composition of A, composition of B, composition of C. If we want to plot them all together, we can combine them. But I will remove the temperature because it's on a different scale. And so we can see A is going up and then down, B is going up and then down, C is just going up. So one could question, why is A going up? It's a reactant. It's because the compositions are given in terms of molar volumes. And therefore, because of the change in density, it actually goes up and then down. This is also exactly the same profile that is given in the book. So, and we can also save this, all these results in a CSV file or a text file, and then we can use any other plotting routine and things like that. We can also restart the simulator from the endpoint of this as the next simulation. So there are lots of different options that one can do. We can close this, and we can also see the detailed results. at the initial point and at the end point. So now we close it here and we can start the simulator again and go to the dynamic. And here, now we can also ask it to generate eigenvalues. So what it will do is at the end of the simulation, it will calculate, or during each of the steps, it will calculate the eigenvalues and put it in a report. So it does the same things. We will just close it and we go to the bottom here and see eigenvalue report. So now it gives the detailed results, and the eigenvalues you can see are negative, which and only the real part, which means that it's a stable system and it will go to a steady state. So all of these are fine. Now the question here is this. Let's go back to the view original model. All these variable values that we had given here, if we wanted to change them during optimization for process optimization or for the parameters during parameter regression, then we need to change these variables during the optimization. And if we write them as explicit equations, we cannot do that. So we need to remove all of these equations. So one way to do that is, if I go back to the my Word document, is that we comment this all out, and then MOT will automatically know that these variables need to be specified, and then we will specify the variable values. So now what I will do is I'll go back here and I will close this. And now I will open MOT again. And go to create model. And now from the Word document, I will put this model where we have commented out everything. So now you can see these are all commented out. So we again say accept changes, accept the model, compounds are not used. Now we have a much smaller list of equations, and now we need to classify the variables. And now you can see that there is a lot more variables. So we need to say again, like before, which is a dependent variable, that is T, CA, CB, CC. And among the remaining variables, we can specify some of them as parameters and the other ones as non-variables. So we will specify first the non-variables, which are T10 is a non-variable, then T0, TB0 also is known, T10, T20, then CA, then CH, then T0, then TA, and T. We can keep T as parameter. It's not a problem. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So, and the remaining ones are parameters. So we have parameters, we have known variables, we have dependent variables. And like before, we first choose the dependent variables, connect them to the differential equations. So now the degrees of freedom are satisfied. And then we can look at, we have to give the values of the variables. So we go to set variable value. Like before, we give 298 and 1. But now we have to give also values of the known variables and the parameters. So if I have chosen correctly, then 1, 2, 3, 4, 5, 6, 7. I think I still missed some. V0. Yes, these two should have been parameters. So we go back to classify variables. V0. And this also. So now 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now they're correct. So now we have to give values for these. So it's quite easy if we prepare them in advance. So I've got these values here. I just copy them and paste them. And similarly for the parameters. Okay, so now all the variables that needed to be specified are given, and we have given the initial conditions. We don't need to worry about dependent prime and explicit. This will be calculated. So now we can set up the solver, but before that, we also need to go to variable chart. And say which variables we want to plot. And so now we should be ready. Now there are two options in addition to choosing the solver from here and also from here. This is to choose the solver, but we can also use the calculation mode just to check each of the equations. So if we click on this, then for each of the equations, based on the values that have been given, which are on the right-hand side of the equation, the variable on the left-hand side are calculated because these are explicit equations. So now we have all the values. Unless we have some strange values, it should be okay. So now we are ready to solve. So let's go to the solver again, and we choose the same dimensions, 0.02 and 340. So now it's set up, and so let's look at the solution. And we put again so here is T, Here is CA, CB, CC, and we combine them. So what is the difference? The difference is now, if I close this and close this, now if we want to do an optimization, the optimization will require to know which variables should be changed. So since all those variables that we have defined as parameters are listed here, we can choose which ones will be active, and then in the loop of the optimization, these variables will be changed. Also, the constraint equations will be given. And also, if we want to give experimental data, like for the temperature for the compositions, we can give them here, which we will show in another example. Also in the optimization, we can choose the objective function and so on. So all of these things can be chosen if we wanted to solve an optimization problem, which will be in another recorded video example. So this was just to show that there are different ways to do the modeling. If we wanted to do the modeling where afterwards we want to use the model object for parameter regression or for process optimization, then we should not use the equations like, we should not give the values of the variables like this. We should give the variable values as set variable values. So which means all these values here can be changed through the optimizer. So this was a simple example on how to set up a process simulation with MOT. And I will close this now. And once we save the file and an MOT object is created, and I will go back now to my presentation mode. So as soon as we save, we just need to save, nothing else. Then an MOT object is saved. And that MOT object can be opened and we can do any simulation, or we can do many other things. So we have property models already developed with MOT. We have unit operation, steady state, reaction, separation, different kinds, flow sheet, Tennessee-Eastman problem, just a simple mixer, reactor, splitter, divider kind of problem, Williams auto plant optimization, and then many others like parameter optimization, model discrimination, partial differential equation solvers. These will be in future recorded videos. So this video ends here. If you're interested in any of these models or interested in using MOT for your study, for your research, you're most welcome to contact us, and we will be happy to arrange a model for a version for you. With this, I end this presentation.